Hello. In this video, I am going to present how is working the simulator we developed with my friend Danjing Li from the Institute of Technology in Shanghai. And it illustrates the result presented in the paper control of discrete event system with resource sharing and uncontrollable inputs. This simulator is this one. You have a simulation of a Petri-net, which is given here. We assume that you know how it's working time Petri-net. We have places, a set of places with a duration, a temporization, which is associated here, for example, 5. It means that the evolution of token in this graph, a token has to spend a minimum of 5 time units before to contribute to the firing of the downstream transition. So in this Petri-net, we assume that we are with internal transition denoted X, output transition denoted Y, and input transition denoted U and W. The red ones, the W, are input transition, which is assumed to be known, but you assume that you can't control the firing. It means that it represents some input here, token, which are present in this case, but you can't control this input. It's like if you think to a manufacturing system, it's furniture which arrive. You can't control when the furniture will arrive. You know when it will arrive, but you don't know. You can't control exactly. Okay. So, for example, in this case, I have initially I have some token in this system like that, and the idea is that I control the input U1, U2, U21, and U22. Actually, this Petri-net represents a production line. You can imagine with the input here, and the line is going like that until the output Y1. Then here you produce some part, for example, on this line, and you produce some other part on this line. These two lines actually they share some resources. For example, machine. Here we have two machines which are shared between this line and this line, and here we have with one machine which is shared between the both line. In this system, we assume that we have a priority policy. It means that the token on this line is with a higher priority than this line. When it's a higher priority line and the lower priority line. It means that if there's a competition for the resource in the same time, the first line will win and will consume the resource. For example, if I fire this input here, I will take, here, I will take the resource because there's no competition, okay? And then I can deal with the availability of this resource. Now, if there's a competition between this transition and this transition, for example, 1 and 2 here, I take the resource for the first, and I take the resource for the second, and now this token has to wait because the resource is taken by the higher priority system. This token will be fired only when the resource is released by the higher priority system. And so I invite you to manage the working with the token. Here I have token if I can simulate to see the behavior of the system when I have many parts in each. Okay, I represent with a black circle when we are a lot of token inside. Of course, here in this case, since the system with higher priority is with full working, all the token of higher priority system will work before to deal with the lower priority system. And we are going to finish the higher priority before to deal with the lower priority. You can see that the resource is always taken by the higher priority system. On this table represents the numerical value, the number of firing of each transition is for U, U1, U12, W, which is assumed to be uncontrollable, the internal transition, and the output transition here. Here I represent the difference between the firing, instantaneous firing of this transition and this transition, and this transition and this transition. It means it represents the internal stock of this place. Here it is 2, and you can see 1 here, 3 here represents a 3 here, 3 token, 2 token. Take a look on this place and see this value in 3 token, 2 token, 1 token, and 0 token. There's no token in this place. And now you have a stock here, and we deal with the lower priority system. Since there's no solicitation for the highest priority, you deal with the lower priority. You can imagine for this kind of system, it can be a manufacturing system, as like I said, but you can imagine that it's also an emergency center with here the arrival of patient with the higher emergency, and here the regular patient with a lower emergency. And here the lower emergency or the regular patient have an access to the resource only if there's no patient with high emergency. So this system is working like that. What are we doing in the paper? We are considering that we have the red transition, which are not controllable, and we want to find the optimal control of the input U in order to preserve the quality of service for the higher priority system and to improve the quality of service of the lower priority system. It means that we are going to control in just in time. It means to minimize the internal token in order to take the resource only when it is necessary in order to leave the resource available for the lower priority system if possible. To illustrate this, I'm going to consider a scenario here, which is given by this free button here. It's a control example where we assume that this furniture, we say that this uncontrollable input is fired only with 5 tokens at time 43, and the other furniture are fired with 5 tokens at time 1. Okay. And if I click here, I obtain this token, and here, without control, I fire immediately the input U in order to deal with this system. And what happens? The higher priority system is managed. We take the resource here, and you can see that the higher priority system takes all the resource, and when it's finished for this resource, we can deal with the lower priority system. But here, since there's no token here, the token is blocked here. It is waiting for the arrival of furniture. And then you have a stock here and a stock here. But this stock, and especially this, block the functioning of the lower priority system. You can't deal with the lower priority system because the resource is waiting for the arrival of furniture. And then now this transition is fired, you have the arrival of the furniture, and then you deal with the higher priority and the internal stock that you have here. So when the higher priority system is managed, you can deal with the lower priority system. So in this case, we represent here the firing of first the 5 token for the higher priority and the output for the lower priority here with 2, 3, 4, and the last is here, and it will occur 4 seconds later, 5. Okay, then you fire first the higher priority and then you fire the lower priorities when you don't have control. Now I'm going to compare this with the higher priority system. Okay, here I represent the two systems, and we are going to compare without or with control. On this side, I will simulate without control, and on this side, I will simulate with control. Okay, I have the time which is working on the both side, and so if I fire here without control and with control here, we can take a look on the behavior. Obviously, without control, you fire immediately you here, then you deal with the higher priority system. Here, we don't deal with this because we know that there's no token here, and then we optimally uh, delay the firing of this transition and this transition in order to leave the occasion and to take the advantage of the availability of the resource to manage with lower priority system. If you take a look here, you are blocked. Then the token here are waiting, and the patient or the part are waiting uselessly because the resource is not coming. Now the resource is coming here on the both side, then you can deal with the higher priority system. Of course, you give the priority to the higher according to the lower priority. Now, for the system without control, you are still to deal with in the same time parallel with the higher priority system, and now you deal with the leaving part for the lower priority system. And in this case, with control, you see that you already finished the lower priority system. You already saved the lower priority system on this system. And here you have to wait to finish. So if it's finished now in 4 seconds, you finish on the both sides. Now if you compare in the numerical value by taking a look, I start again, and here I only give the simulation of the here. I only represent the simulation of the system with control, okay? I don't deal immediately with the firing of the higher priority system, okay? Here I have the firing of the output without control and with control. Without control, with control, without control. With control here, we have finished 2 parts for the lower priority system at this instant, 3 parts, 4 parts, 5 parts. We have finished to manage the lower priority system, and we now start with the higher priority system. Here, with control and without control. It's the same value. You don't reduce the quality of service for the higher priority system, but you improve the quality of service for the lower priority system because you take advantage of the availability of the resource. Okay, then now you have finished all for the controlled system, and now for the uncontrolled system, you manage for the lower priority system by dealing with the token which was waiting inside. It is represented on the other simulation. 3, 4, and 4 seconds, we will finish the last 5. So, if I show you it again, we can focus on the simulation, the same simulation, we can focus on the internal stock. It is the value of the number of tokens in this place. In this, with control, we are with 0 token, but without control, we are with 3 tokens here. It is not shown on the simulation because it's on the other window. And for this place, you have the same evolution of the stock. And in the same way, here we are dealing with the lower priority first because the resource is not available on this place. Now the resource is available, you fire immediately the higher priority system. So both are equal. So I'll leave you take advantage of this simulator to manage the evolution of the system, and you can work with this scenario to well understand the problematic.